Hello guys, today I'm going to give you a brief introduction into organic chemistry. Really, what is organic chemistry and what do we need to know prior to organic chemistry, and just kind of give a brief introduction to IUPAC nomenclature, so basically naming basic alkanes and functional groups, and really just get you guys started in organic chemistry. So you guys will be prepared for the first day of class and really, in this whole video series that I will be doing, I will be teaching organic chemistry from the ground up, covering every topic. And make sure you guys check out my website as well. There's a lot of resources on there. I do have a rough course schedule that you will see in a regular organic chemistry course, and there are also several practice problems that you can do, and really a lot of my work and a lot of my videos will be archived on there so you guys can get more of an insight on why I'm doing this and really to really help you guys do well in organic chemistry. So, what is organic chemistry? To simply put it, it is a subfield chemistry that focuses on hydrocarbons, and more specifically, it's really about these carbon-carbon bonds and these molecules that are made of carbon. And really, that is they call this organic chemistry, but it's just the chemistry of everything you see in this world. The plastics and the clothes that you wear is all organic chemistry, and the medicine that you may be taking, your aspirin pills, your, pain medications, sleep medications, this is all organic chemistry. And really, we're going to talk about this in this class, and you guys will understand why certain drugs have certain biological effects and why certain plastics have different types of properties, and really organic chemistry is true chemistry compared to what you guys learned in general chemistry, where we really just talked about the atoms and the electrons. But in organic chemistry, we're going to apply those subjects and apply all the knowledge that we know from general chemistry to have a broader perspective in the chemistry that really surrounds our world today. So here I like to point out an example that is pretty interesting here. And so this is a molecule of carvone, and carvone is actually an essential oil that's found in spearmint and also caraway seeds. But here I'm displaying two different isomers, and these are optical isomers, which we'll be covering throughout the course. But for now, you just have to understand that these are mirror images of each other. And if you see the left and right molecule, they are mirror images of each other. And if you had a plane down here and imagine as a mirror, and you look at this molecule here and this molecule here, we can really see that these are just mirror images of each other, and they're basically identical, just like your left and right hand. But here, even though they look exactly the same as molecules, they have very different effects. And our carvone is used in spearmint. It's an essential oil, and it's basically used as a flavoring agent, and we see S-carvone, which is found in caraway seeds, is actually used as a mosquito repellent and is a registered pesticide by the EPA. So we could really see the big dramatic differences that organic chemistry really wants to cover, right? And this is just purely, we're talking about isomeric differences, right? They look exactly the same, but they have drastically different effects. And we can see how this can be really important, right? Because now, let's say we're constructing a medicinal drug and we have different isomers, and let's say we have mirror images, right? They can have drastically different biological effects. And this is why organic chemistry can be really important in, let's say, the medical field or the pharmaceutical industry, right? And so I feel like this example really captures uh, uh, the introduction of organic chemistry, right? So now we're going to go into basically the general topics that were covered in general chemistry while you guys took it before organic chemistry, and some of the things that will be constantly used throughout the course that you'll probably have to recollect. And so here we're going to go into molecular orbital theory. And so molecular orbital theory is something that was covered in general chemistry and is basically a way to introduce how to visualize bigger compounds, right? And really, in this course, we'll really be using this language like sigma bonds, pi bonds, and p orbitals and s orbitals, and why that actually determines and really helps us visualize the structures of huge, huge carbon compounds. And we'll later you guys will find out why this is actually very important and how it has a very dramatic impact in organic chemistry. So here we're just going to review basically what a sigma bond and what a pi bond is, because those are the two classified bonds that we learn in MO theory. And basically it's very simple. If you guys remember, sigma bonds is basically a head-on overlap of two p orbitals, or one s or one p orbital, as we display down here, right? We really see that these are two p orbitals combining, whereas we see one s orbital and one p orbital combining. And basically, we can classify this as a sigma bond because it is a head-on overlap, and we see that there is no nodal plane. Whereas, opposed to a pi bond here, and a pi bond really describes a double bond, right? When we have a molecule kit and we see, even in line diagrams, we see that this is a double bond, right? And that's what we learned in general chemistry, and a triple bond looks like this, right? And we kind of see a representation of this in a pi bond here, right? In a pi bond, we see that there is a nodal plane right here, meaning that visually what it really looks like, right, if you had two carbons, you just have these huge lobes here, and you have this plane in the middle, and we call this a nodal plane, and this describes one pi bond. And a pi bond can only be made with two p orbitals overlapping side by side. So, like stated here, only forms of two p orbitals, and we have this internuclear plane. Okay, and so again, we can really visualize this, and these are two sp3 hybridized orbitals, if you guys remember that language, and we'll cover that next. But basically here we have this modeling of a pi bond forming with these two p orbitals, right, coming from this compound and this compound combining to make this nodal plane overlap here. And I kind of represent here these electron configurations here, right? These electron pairs, because that's what's really happening when we're modeling this. Okay, and so this is a model of ethene, which is ethane with a double bond, right? So the simplest alkene that you'll find in organic chemistry. So like I touched a little before, was hybrid orbitals. What are hybrid orbitals, right? And we kind of learned in general chemistry what hybrid orbitals are, and there's a classification of atomic orbitals. Basically, we're combining them and hybridizing the two different orbitals we see, s and p, and we're basically coming up with this theory called hybrid orbitals, right? We have sp orbitals, so if you had one s orbital and one p orbital, we have this sp orbital, and that is represented as a linear structure, and we learned that this can be formed with a triple bond, and that's what we see here. We see an R group with a nitrogen triple bonded to a carbon, right? So this kind of represents what an sp looks like. And then same goes if you had two p orbitals and one s orbital, we have an sp2 hybridized orbital, which is trigonal planar, and it's represented as here. And really, this dotted cloud here is this p orbital that's sticking out. And in organic chemistry, we'll come to find that these p orbitals will always exist in these carbon-carbon bonds. And so it kind of represented this trigonal planar structure here with this ketone group, and with these two R groups attached to this, and this is what you'll commonly see, and we'll classify this as sp2, right? And so moving on to a tetrahedral structure, which is sp3, which is three p orbitals and one s orbital, and we have this tetrahedral structure, and we kind of represent it as this regular methane, right? Very simple, and it kind of looks like this if you were to draw this out with the wedge and dash diagram. And so, I mean, this is basically what we'll be using a lot in this class to describe acidity and S character and electron clouds and shapes, and it's really just going to help us model and visualize molecules. So I highly suggest that if you do not understand molecular orbital theory or hybrid orbital theory, like I just covered, if you don't understand what I was saying, then just please go review that, because it is a very in-depth topic, but basically we're just using it to describe shapes and electron clouds, and that's really just going to help us later down the line. Okay, and so now we're going to come into IUPAC nomenclature, and so this is basically the universal language for organic chemists to identify molecules, and it's a way to essentially name organic compounds. And an association that has this huge rule book that basically tells us everything to know when we're naming a compound. And really, if we see a compound, or if we're given a name of a compound, we can easily draw it out and easily visualize it. And this is why this nomenclature can get complex, but there's basic nomenclature that we have to understand first. And I'm sure many of you guys have covered this in general chemistry briefly, and that's what I'm just going to review, because we will go in depth, and I will make a separate video on just IUPAC nomenclature. But basically today we're just going to talk about parent alkanes, and really this parent alkanes even goes for alkenes and alkynes, and we just have to know. Basically, it tells us how many carbons are in this molecule. Okay, so alkanes again are basically single bonded carbon-carbon chains, and the suffix ane is basically included when we're talking about single carbon-carbon chains. And then the prefixes again are all the same, whether it's an alkane, alkyne, or yeah, that's about it. Yeah, so basically it's determined by the number of carbons. So we have methane, ethane, propane, and butane. So these four really are the ones that we have to remember. And we have to remember that methane is 1 carbon, ethane is 2, propane is 3, and butane is 4. And really there's no easy way to remember it. We just have to remember that propane is 3, butane is 4, ethane is 2, methane is 1. And then everything after that really is simple geometry, because pentane, right, like a pentagon is 5, hexane, hexagon 6, heptane, right, 7, and octane's 8, like an octagon, and nonane is 9, and decane is 10. And really in organic chemistry, the biggest molecules we'll really go up to is decane. I mean, anything larger than that, we don't really have to know. Okay, and so again, methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. If you guys remember that, really, this is the basic and the easiest part of IUPAC nomenclature. And if you guys understand this, then you guys already understand a large part of naming structures. So I kind of want to give a little introduction into that, because maybe first day of class we'll talk about methane or ethane, and you guys will they already expect you to know how many carbons are in those bonds, right? So this is a very basic introduction. So basic notations that are being used in various textbooks while you read them, and I'm sure some of you guys might get confused. So basic nomenclature, we'll use X when we talk about in the textbook, especially when you're reading, they'll talk about R groups and X groups, right? And X always represents a halogen, which is a group 8 noble gas or halide. And that's represented by X, and R in this case, any carbon is always going to be represented as C, right? And any R can be any substituent. It can be a longer carbon chain, or it can just be, anything that's not a halogen. So yeah, or a functional group. Okay, and now we're kind of get into line structures. Line structures are basically a way of avoiding Lewis dot structures, right? We don't want to draw every single carbon and every single hydrogen bond where we could just represent it as a line. It's very easy, right? And so each the end of each point represents a carbon and then the maximum number of hydrogens, the saturated amount of hydrogens attached to that carbon, unless it's noted otherwise that there is another substituent attached to it. Really, we're just assuming that there's going to be, in this end, there's going to be three hydrogens, right? It's a CH3 single bond to another CH3, a methyl and methyl bond, which makes a ethane group, and we just represent that as a simple line. But let's say butane, right? Each point represents uh, a carbon, and we know butane is a 4-carbon chain, right? And simply, butane is just this line structure, and it's always going to be written as a zigzag, and we'll come to really find out why it's always written as a zigzag. And yeah, so basically hexane, same thing. Each point, 1, 2, 3, 4, 5, 6, right? There's 6 carbons in hexane, and then each endpoint is already represented of how many carbons that, or how many hydrogens that can be present there. So in this case, these endpoints will be 3 hydrogens, right? CH3. However, this, since there's a double bond, or since there's 2 bonds adjacent to this carbon, we essentially have to put only 2 hydrogens here, right? So it's already assumed that there's going to be 3 hydrogens here, 2 hydrogens here, 2 hydrogens here, 2 hydrogens here, 3 here, and 2 here, right? And as time progresses, you'll get very used to understanding that, and really just something that will come to you when you do more practice problems. And so again, propane, 3 carbons. And so the easiest way to really draw this out is they give you, let's say, draw heptane, right? I represent that as you can either start with 1 and say this is 1, and then 2, and then count it individually, and then kind of get confused, 1, 2, 3, 4, 5, 6, and then 7. Or you can just use this trick that I use is if they ask for heptane, we understand that there's a 7-carbon chain, meaning that we should just draw 6 zigzag lines. So always 1 minus the number of carbons in that molecule to draw that line structure. And so let's say we need to draw octane. Just draw 7 zigzag lines, right? So 1, 2, 3, 4, 5, 6, 7. 1. So if we count the carbons now, it's 1, 2, 3, 4, 5, 6, 7, 8, right? And we're supposed to draw octane. And this has 7 lines. So always 1 minus the number of carbons in that molecule. Okay, and then later on we'll be introduced to cyclohexanes and these cyclo structures, and basically what that means is they're just ring structures. So anytime you see a cyclopentane, it's just a pentagon, right? It's a 5-carbon ring. And a cyclohexane, right, very commonly seen as a hexagon, and you'll really see this a lot in organic chemistry, cyclohexane. And really there's a whole unit where we talk about cyclohexane, and you'll come to understand why this is so important. And some of the other rare things you'll see is cyclobutane and cyclopropane. And again, we'll understand why these cyclo structures are very rare to see, and it's very common to see cyclohexane, and we'll understand why. But for now, we have to just not be caught off guard when we see these weird looking structures in maybe throughout the textbook as you read. And so we'll kind of also get into basic functional groups, and depending on your professor, they either expect you to know this at the beginning of class because it was covered in general chemistry briefly at the end, or some professors will spend a lecture going over every single functional group. Either way, it is just good to know the basic structures beginning instruction, because it's sometimes it'll be thrown around, and really just you don't want to be caught up in something that's pretty basic to understand. Okay, and so functional groups, again, like we mentioned before, these R groups can represent anything, any substituent that's not a functional group, basically. Okay, and so it could be just, this could just be a longer carbon chain, right? So an alcohol is always represented by a hydroxyl group, one hydroxyl group, so basically an OH group. And something we briefly covered why this is important, a lot of alcohols undergo a hydrogen bonding, right? OH groups just bonding, having these intermolecular interactions. And so an alcohol is always this R group attached to a hydroxyl group. Um, and we get to ketones now. And actually, ketones is very basic. If you see this alone in a molecule, we'll call this as a ketone. But really, this basic ketone structure, if you were to replace this with a nitrogen or an alcohol, will change it into a different functional group. And so really, instead of calling this a ketone, we usually call this carbonyls, because this carbonyl is basically this uh, class of functional groups, right? Carbonyl-based functional groups is what we call it. And so one carbonyl-based functional group is carboxylic acid. And we understand this is a carbonyl base because we see this double bonded ketone group that's attached to an alcohol, and that makes it a carboxylic acid. Uh, Something to also remember about carboxylic acids is they're always going to be at the end of a compound. Um, and that just really has to do with the hybridization structure and also basically the octet rule. And so now another ketone, or not ketone, another carbonyl-based functional group is aldehydes, which is just a ketone with a hydrogen, and another one would be an ester, which is essentially um, a ketone with an oxygen group, and another one's an amide. And this R group here, and this amide represents, again, any substituent group here, and really, um, this can turn into a secondary amide. And we'll really get to what primary and secondary and tertiary groups mean, but for now, it's just a language that will be used throughout organic chemistry, and we'll come to cover that later on. And then these are amines, and amines are basically just nitrogen groups attached to other substituent R groups. And basically that's it. This is a brief introduction to organic chemistry. I hope it helped. Like again, please check out my website. Give this video a thumbs up, like it, share it, subscribe to my YouTube channel.